there folks, Mr. G here with another educational video. This is part 3 of our Chapter 6 crash course. Here we're going to be talking about solving rational equations. Now this is something that we talked about before back in Chapter 3, but I don't think it was very clear to everyone. So we're going to go over them again, remind you how to solve them, and go over a few weird cases that we haven't talked about before. The 3 main steps involved in solving rational equations are to first state the restrictions. We talked about that in our first video. We are then going to find what polynomial to multiply both sides of our equation by in order to clear all the denominators, and then we just solve it. Once we get to this last step, it's just like we did in Chapter 3, but we do have to be careful to exclude the restricted values that we said in Step 1. Those ones can never be our answers. If we wanted to start by solving this equation here, our first step is to state the restrictions. In this case, there's only one, that x can't be equal to 4, because we have x minus 4 in both of our denominators, and we can't let those be 0. Next thing we want to think about is what polynomial we should multiply both sides of our equation by in order to clear our denominators. In this case, it's pretty simple. We multiply everything by x minus 4, and that will cancel out both of our denominators here. Don't forget we need to multiply our x minus 4 by our x here, because it doesn't have a denominator, it doesn't cancel out, but we're still multiplying it by each part of our equation. From here, we can rearrange our equation, get everything onto one side, set the whole thing equal to 0, and then factor it. In this case, we want to find our 2 special numbers that multiply to give us -6 and add to give us +1. So 3 and -2 in this case. So that's what it looks like in factored form. The key to remember here is that if either of these are 0, the whole thing will be 0, and we'll have solved the equation. So solving each individual part equals 0 gives us our 2 answers, and since neither of our answers conflict with our restriction, both of these are valid answers to our original equation. If we want to check our answers here, all we need to do is plug them back into the original equation, which is this one right here. Once we've plugged in our value of -3, we can start simplifying. Since we've got negative on top and bottom, this would be positive. And this -3, we can turn to have a denominator of 7 by multiplying top and bottom by 7. And now we got both sides to match, so we know we have the right answer. We can do the same thing with x equals 2. Plugging in our values, now we can do some simplifying. This would be -3, this is -5. We get both sides to match, so again, we know we have the right answer. If the question asks you to check your answers, this is what I'm expecting, but we don't have to check all of our answers. This is just a good thing to do if you have the time. Let's imagine we want to solve a slightly harder example. Here, if we want to state our restrictions, remember we have to factor any of our denominators that don't just have a single power of x like they do on the left 2 here. So we need to factor this polynomial, -5 and +1, and you'll notice that we have the same 2 things on the bottom here as we have each individual on those sides. So our restriction is going to be that x cannot be 5 or -1. This is also very helpful for our second step, which is to find a polynomial to multiply both sides by in order to get rid of all of our denominators. If we multiply both sides by x plus 1 and x minus 5, we'll cancel out these 2 denominators as well as this denominator, but there will be a little bit left over on these 2 terms. We'll end up with an equation that looks like this. Once we distribute in our x and our -3, we'll end up with this expression, which gives us this as our final polynomial once we've moved everything to one side. Our 2 numbers are -5 and +3 in order to factor this, and we can look at each of these 2 individually, figure out when they're equal to 0, and these would be our 2 answers. But wait, remember we have to check restrictions. If we go back up and check our restrictions, we see that x cannot be equal to 5, otherwise we end up with 0 in our denominators here. So that excludes this answer based on our restrictions. So our only answer for this question is x equals -3. Our last 2 examples are kind of weird cases where we're going to find that the x is going to disappear from all of our equations. And what I want to show you is how we deal with that and how we can interpret our answers. Let's say we want to solve this equation here. Once again, we start with our restrictions. We can see we've got 2 different denominators, and our restrictions are going to be that x can't be equal to -3 or +1/2. At this point, we can multiply both sides by a polynomial. This one here makes the most sense because it allows to cancel out both of our denominators. We will be left with a little bit on top once we multiply through, however. You should end up with something like this. We can distribute our 4 and our 2, and we'll move all of our numbers over to one side, and you should get this, which is a bit puzzling. There's no x's left over. How are we supposed to solve this? Well, the first thing that should tip you off is to think about when is 14 equal to 0? And the answer to that question is really simple. It's never equal to 0. 14 and 0 are different numbers. They're never going to be equal to each other. So what we have here is a contradiction, and what that tells us is that we have no answer. There are no values of x that make these 2 sides of the equation equal to each other. If we graph this on Desmos, what we see for our two functions is that they never actually touch each other. It kind of looks like they're touching each other in these two places right here, kind of as they go off on the right and the left. But if we take one of these points and we zoom in, we can see that there's still a difference between the two of them. It's just getting smaller and smaller. But that distance is never going to actually close. So these two graphs never intercept. There's no way we can make them equal no matter what values of x we choose. Here's our last example. Again, we want to start off with restrictions, which means we need to factor this denominator over here. We have a common factor of 2 and x, which gives us this polynomial down here. This allows us to see our restrictions, that x can't be equal to 0 or 7. Like before, we want to multiply through by a polynomial. These two work really nicely because it'll get rid of all of our denominators. We can distribute and simplify. Once we distribute, we can move everything to the left side here. And what we'll end up with is that 0 is equal to 0. When is this true? It's always true. 0 is always equal to 0. It's the same number. But just like our other cases, we got to be careful about our restrictions. So this is always true except where we're not allowed to have our x values. So our answer is that x can be any real number except 0 and 7, because those are our restrictions. That's where this function isn't well defined. If we graph this on Desmos, it's kind of hard to see because these two functions are right on top of each other. So they're occupying the exact same space. The only places where we can't graph it are where it shoots off to infinity, right at these lines right here. So right at these boundaries right here, you'll notice we get really, really close at x equals 0, but we never actually touch x equals 0. We get very, very close to it, but then we end up shooting off to infinity. So these are always the same except for these two places at x equals 7 and x equals 0, where it's not well defined, where it shoots off to infinity. We get a divide by 0 error. Now these spots have a special name. They're called asymptotes, and we're going to talk about them a little bit next time when we try and graph rational functions. That's the end of our video here. Thanks for tuning in. Stick around to next time where we're going to talk a little bit about how we would graph these rational functions like Desmos does, without, of course, using Desmos. I'll see you then.